Start. Any suggestions? So we didn't find it actually. We just basically none of these quantum numbers we rigorously showed, right? We just said these are quantum numbers. There is like n, l, and m, and there is a relationship between them. It's like l is supposed to be less than n minus 1, and m is supposed to be running from minus l to l. These are just two rules. No, this can be shown, but you need to go and study a little bit special functions. There are also sometimes semi-classical arguments. I may or may not show it, but I think for me the cheapest way is just look at these rules and remember them because they are so simple. And if you use it just a couple of times, you remember them, right? I think this is cheaper. The arguments, in my opinion, they are a little bit more expensive. You have to put a little bit more effort, and it may not help you apply it, right? Just because you know how to derive it doesn't mean you can use it. At the moment, I think, at least in this course, we are aiming to just be familiar with how to use these numbers.
So they come from these defined formulas.
It is what?
We can find this relationship from this formula.
Exactly. Without any assumption, you can find them from the solution of the differential equation. Exactly like particle in a box, right? You solve it and you find energies at certain levels and nothing else is allowed. Exactly like that, there will be constraints coming from the differential equation. Or like harmonic oscillator, right? We said that the energy is supposed to be h bar omega n plus a half. We showed a semi-classical argument, which was actually more complicated than the result itself, right? The result is so simple, it's like h bar omega n plus a half, whereas in the semi-classical argument, you have to remember the Bohr quantization. You have to think a little bit about how do I mean, of course, it helps us understand where it comes from, but sometimes we may not need it. I think my suggestion here is let's just focus on how these numbers manifest themselves in applications, because applications are actually the real source to learn how this thing is behaving, in my opinion. But of course, there are other courses, they're teaching partial differential equations. They are teaching you how to solve these equations, special functions. If you have the appetite to learn in that area, you have plenty of options in this department. But we have a lot of things to cover, I think. Of course, this is interesting, but I think there's more interesting things coming. So let's not be distracted. Take what I tell you and just push forward just a little bit. So I want to finish this last time we were talking about angular momentum, and I couldn't finish the last piece. Let me finish that, and then I'm going to be talking about these quantum numbers more. Let's think about angular momentum. So the angular momentum is classically L is equal to, if you know MVR, it's baby angular momentum. Now we are specialists, so we have to do real angular momentum, and for the real angular momentum, we have to have these vectors, and we have to have this cross product. And when you go to quantum mechanics, P is just going to be minus I h bar nabla. So to simplify, let's consider 2D motion, which will be enough for us to see what this thing does. And for that, let's think about polar coordinates. Maybe something like that. So So this is, let me call this rho, and let me call this one phi, and like, okay, this one is y, this one is x, and I think everybody knows x is equal to rho cosine phi, and y is equal to rho sine phi. And I am interested in the z component of this thing, so let's look at the z component. L is equal to, how do you calculate cross product? Just look at, I don't know, x, y, z, minus I h bar del x, maybe not to scare you. Okay, let me write it in more detail. So I'll put the minus I h bar in front. So this is going to be del x, del y, del z, and this is, I think, however you calculate, this is fine. I only need the z component, right? For the z component, I'm going to have minus I h bar. So x del y minus y del x. Okay, so this is, if you want, z component. This is z component. Any questions? So far I didn't do anything. So now I want to look at, let's, because of it's right in front of us, let's look at this del phi. Let's act this on a function of x and y. And we are just going to use the chain rule, and the chain rule says it's going to be del x, del phi, del f, del x, right? Del x cancel, I have del phi, and the other one is del y, del phi, del f, del y. Again, del y's cancel, I have, so this is simple chain rule. And from del x, del phi, I have rho, right? Rho, derivative of cosine is minus sine phi, del x, f, but rho sine theta is y, right? Plus del y, del phi, y is here, it is going to be rho cosine phi, del f, del f, del y, but rho phi is here, this is x, and this exercise shows that this is minus y del x plus x del y, this entire thing acting on function f. And from here I can see by comparing this, so here is my angular momentum Lz, so let's copy this. So this is my Lz, I think I couldn't copy the minus, it's here, but you can see this thing is, if you want I can put minus here, well I think I don't put minus there, I just replace x and y, so I'll take x to this side, y to this side, and erase this, put this back, and compare. Right, this is x del y minus y del x. This is del phi, x del y minus y del x, and this is minus I h bar del phi. And now, okay, I can identify my Lz with minus I h bar del phi. So we can also do exactly the same calculation in 3D. So in 3D, and the result will be same, but let me show you how to get that. So here is my coordinate system, something like that. And I have like a vector, something like that. So this is R, and it has like some projection on the plane, something like that. So this is theta, and this one is phi. And in the spherical polar coordinates, we can also identify unit vectors exactly like we identify unit vectors. So this is r hat. So the theta vector is like along here. So this is my theta vector, and phi vector is like into the page. Like if you want, so this is okay. I think into the page is something like that. And I want to calculate L, which is R cross P, and I want to write R and P in these spherical coordinates. R is equal to R hat, and P is going to be equal to minus I H bar. So there is like a nabla inside, right, with minus I H bar nabla. But nabla is what? Nabla is, I can have a derivative in x direction plus I can have a derivative in theta direction, but the change in theta direction is r, right? This is theta direction del r, I think this is r d theta, and plus, let me push that a little bit, phi hat 1 over, and the change in, okay, there's like a great circle here, and there's like a meridian here. For the meridian, the change has to be r theta, so the partial derivative comes with del r d theta, and similarly, here's r, I think, sine theta, del phi. Okay, so this is my operator. It's a little bit complicated, but you have to think a little bit more. And we are interested in R cross P, and it is Z component is what we want. And R has R unit vector, right? You are going to, so these unit vectors like behave exactly like Cartesian unit vectors. You have, for example, R cross, theta is equal to, okay, this is R, this is theta. So you can imagine this to be X, this to be Y. X cross Y is going to give you Z, but in this little coordinate system, Z is along theta direction, and you can cycle it. For example, push theta here, cross R is theta dot, and one more cycle, theta dot, cross phi is R hat. So now I am going to write this thing, so this is, you can see R cross R is going to be 0. And I also need to do one more thing. I need to calculate the Z component. So for this, I'll just take L with unit vector along Z. And what is the unit vector along Z? So this is the Z direction, if you want. So this is my R unit vector, and perpendicular to R, I have this theta, so this is R, and my Z is like this direction, so this angle is theta, these guys are perpendicular, so Z, my Z vector is cosine theta times R vector minus, okay, this is theta, this is 90 minus theta, but cosine of 90 minus theta is sine theta, and this is sine theta, theta dot. Then, okay, here LZ is equal to this thing. Okay, let me push this entire thing a little bit. And I dot this on the R cross term here. So, but like let's calculate the R cross term here. So this is, so let me, okay, this thing I can take it here. So this is LZ, and I want to calculate this thing, and this thing is what? So this is minus I h bar. So R cross R is 0, so I don't have to take that. So this is going to be R cross theta hat divided by R del theta plus R cross phi hat divided by R sine theta del phi. But R cross theta is here. Where is it? R cross theta. This is phi hat. And the other one is R cross phi. R cross phi is minus theta hat. And now I'm going to take a dot product between this object and this object. There is no R component inside, so this is going to be 0. And I only need to take theta component. As you can see, there's only theta here. So there is dot dot dot. So this entire thing is going to be minus sine theta, this one. And I'm going to write minus I h bar. So this is this one. There is minus theta, and there is minus here. Okay, this minus is there. Minus theta, dot theta is minus 1. I got this one. This is R sine theta, and this is del phi, right? And I think I missed a R factor here. Oh, this is, okay, so this is R cross P. There's actually, this is R times, and this is R times, right? Because I am taking R cross with P, so this is R, so there will be an additional R here. So basically this cancels this R cancels this, and there's two minuses plus one more minus, and this is going to be minus I h bar del phi. So which is exactly like what we did in the simple one-dimensional case. Okay. Then so LZ as an operator is minus I h bar del phi, and phi is this azimuthal coordinate, and let's act with LZ on the wave functions we found. So phi derivative is going to act on phi functions, and if you remember, we found this like this: a times e to the I m phi, and m was equal to 0, plus minus 1, plus minus 2, and so on. Now LZ times phi of phi is equal to minus I h bar del phi, and this entire thing is going to copy, and you can see this is going to bring in im, and there's minus I, it's going to be plus, and it's going to be h bar m phi of phi. We missed, oh, I put this entire thing is phi, so I put the phi itself. If you want, this is like still a times e to the I m phi. Okay. Any questions? Yes. Yes.
So you wrote L as it's the scalar, so it cannot be equal to cross product.
So okay, let's. What I did is like this is the full L vector, and this is R cross P, right? There is like two vector components, and I take Z projection of this by the Z hat. And L dot Z, this is scalar. So this is basically Z component of L, which is scalar. It doesn't have any vector component. Is that what you ask, or is it?
Yes, but U equal to R cross P.
I equal to R cross. So this one is vector. This one is vector. This one is vector. This is also vector, right? There is like a vector here and this vector here. And I take dot product of these two objects. A vector dot product with another vector is going to be scalar. And you can see R didn't play any role. I only need to take product of this object with this object. And it doesn't have any vector because it's the component of a vector. Okay. Thanks. Okay, now, hopefully you are convinced that M is an angular momentum projection based on all these rigorous calculations. Now let's combine everything we know. Okay, now full angular dependence is of psi is inside this y, Lm, theta, and phi. And these are so-called spherical harmonics. And what the picture we had last time was something like this. We had like this constant angular momentum sphere, but I'm just drawing it in 2D. And here's my z coordinate. But this is my z, and this is my plane perpendicular to the z coordinate. And I don't know, there is like some angular momentum vector like this. Of course, we know this representation itself is misleading, right? We discussed at length, you can never point angular momentum in any given direction, so you have to take this picture with a grain of salt. But what we said is like, so this is the L vector, right? And it is projection, here is LZ. And the full description of system is like this. I can have square of L acting on YLM, theta, phi, and L square was found to be H bar, L plus 1, Y, LM, theta, H bar squared, thank you. And the second one is LZ acting on this, Y, LM, theta, and phi is equal to H bar M, right? Go to the function and ask for M, and the function is going to give you M, and put it there as the eigenvalue. Y, Lm, theta, and phi. So we called, okay, from here we set L orbital quantum number or angular momentum, and its value is L can be 0, 1, 2, dot, dot, dot. And M is, we call magnetic quantum number because we related it to magnetic moments. So this is magnetic quantum number, and its value is M is 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. Any questions? Maybe I can give you just a couple of those spherical harmonics. For example, Y, 0, 0. Theta of phi, but let me not write theta of phi every time to save some time. So this is 1 over root 4 pi. So this is constant. So y 1, 0 is equal to, so this is 3 over 4 pi cosine theta. Y 1 plus or minus 1 is equal to minus or plus exactly the same factor times e to the I plus or minus I phi. Maybe I can write the second one. Y 2, 0 is equal to root 5 over 16 pi, and this is 3 cosine squared theta minus 1. So if you, like, for example, designate x for cosine theta, you can see these spherical harmonics are like polynomials in this x. If you say x is equal to cosine theta, okay, this is not coordinate, maybe u is equal to cosine theta. These are going to be polynomials. First you have zeroth power of u, here you have first power of u, here you have second power of u. If you remember, we had exactly the same thing for the eigenstates of harmonic oscillator, right? They also had polynomials in them.
I
I mean, it is the name of these special functions, right? Like, for example, sine and cosine. What is sine and cosine? It is a name we give to a function we use very often. So these functions you may not be using very often, but they also have a name. They are like sines and cosines, but they are a little bit more complicated. And of course, I don't expect anyone here to sit down and memorize this. I'll give these if I want you to work with them. And the point is, they're like simple cosines and sines. At least the first few of them are very easy to work with. Any questions? Now we can think about electron probability density. So let's electron probability density. Now the key is now in the Bohr model. I think you were asking about that, right? In the Bohr model, we had these like classical orbits, like we put circles and we put like integer waves on these circuits. So the orbits in the Bohr model, so orbits in Bohr model are promoted to these complicated functions of r, theta, and phi. Are promoted this psi n, l, m, function of r, theta, and phi. And when you want to calculate probability density, so this is what we do with psi squared, and psi squared is going to be r squared times this uppercase theta squared times uppercase phi squared. But phi squared is of the form e to the plus or minus I m phi. And when you take the norm, it is going to be 1. So no phi dependence in probability density. And we are generally interested in the probability to find an electron at a distance r from the nucleus. And for that, I have to like specify the volume element. So dV is equal to, I think everybody knows this. This is the r square sine theta, dr, d theta, and d phi. Okay, let me d phi. Then probability to find an electron at a distance r is, we show it like this, PR dr is equal to, so what I need to do is, okay, right, I need to take all possible r's, and there's like a volume element, so this is going to be, so this r square is going to be here, there is going to be this r, let me write n and l, right, this one depends on n and l, this one depends on L and M, and this one only depends on M. R squared, and I need to integrate over all angles because there is no angle here. And this is sine theta, d theta, d phi. And because the norm of this thing is 1, there is no trace of this function, and there will be this function. And the nice thing about these functions, they are normalized. Okay, so this entire thing, if you, okay, for example, if you properly normalize phi, there will be this root 4 pi's here. That will be sufficient for you to put 1 here. And because of this dr, I need to put dr here. And now you can, for example, go and look at a few of these functions. Okay, let me write some of them. For example, r 0, 0 is, let me write the whole thing. This is 2 over a naught, 3 over 2, e to the minus r over a naught. Let me also give you r 2, 0, which is, okay, there are some constants. Let me not write those. It's like 2 minus r over a naught. Yes, e to the minus r over 2 a naught. Can you say one more time?
The direction should be in volume V, find probability in a volume, I think, but you write VR.
So this is probability to find an electron at a distance r. So right? So if you have like a sphere, like there is like a distance r, but you have to integrate over all angles. And that integration gives you 1 because these functions are normalized. And what remains is the r squared. So all you need to know is like take this function and multiply it with r squared to find the probability to find an electron at a distance r. Of course, if you are interested in angle-dependent probabilities, you can do that too. Just don't take integrals. Look at the angle you want, and it's going to give you that. Which I'll show you pictures maybe in a second. Yes.
What do those indices represent also?
So this index is like, this is n is equal to, okay, I think this is 1. Thank you. So this is 1. This index is L is equal to 0, right? This is n is equal to 0, L is equal to 0, n is equal to 1, L is equal to 0. This one is n is equal to 2, L is equal to 0. And you have infinitely many functions like that. Again, you don't have to memorize them, like there are like tables. You can just look at these tables and work with them if you want. Here's like a little exercise for you. For example, exercise. Using this probability distribution, find most probable R for n is equal to 1 and let's say L is equal to 0. Also, so we can look at the function and like optimize it, right? There will be a peak in the function, and this problem is asking you to find the peak, and we know how to find the peaks of functions, right? Take the derivative and set it equal to 0. But we can also calculate, for example, expectation value of R, which we showed with R. What you are going to do is you put this R inside this probability, right? And you are going to integrate. And what should be the result? At least as an order of magnitude comparison. What do you think the expected radius for the electron in terms of A naught? Yes? Exactly. Something like A naught, right? It's actually not exactly A naught, and you can ponder about this if you want. You can also calculate expectation value of 1 over R. And what do you think this can be? Again, there's only R, there's only A naught. This is 1 over A naught. You can calculate these things if you want to exercise a little bit integrals. So now let me show you these functions a little bit. It's not hard to learn. For example, here I defined like something and it's like spherical harmonics Y. Not very hard to like guess. Even if you didn't know, you can just Google it, spherical harmonics in Mathematica, and I copied and pasted it here. And to make it like easier to run, I defined some functions. For example, let me show you the first one. This is like 1 over 4 pi, the one I showed you. And I can, for example, do like 3-dimensional, right? I can hold it and like poke it around to see how it works. I can look at 1, 0 function. This is exactly what I showed you. This is cosine, and I can draw it. You can see this is kind of like a dumbbell, and I call this PZ because this is L is equal to 1, right? M is equal to 0. So I don't know, kind of not bad. You can look at 1, 1, for example. It is, which I wrote, e to the I phi sine. And if you plot it, it's like a donut. I call this P plus because this is e to the I plus here. And you can look at the -1, right? And then you can draw the -1. It is exactly like that because the overall phase difference, when you take the norm, you cannot detect. But what you can do is like you can combine this P plus and P minus just like that, right? Take 1 plus the other one and take the absolute value, then you are going to have this dumbbell in the y direction. Or you can take their difference and draw, and you are going to have this dumbbell in the x direction or y direction. And you can go to, for example, 2, 0 theta. It's like looking nicer but more complicated, right? You can see, I don't know, it looks like a baby pacifier. I don't know. You can look at the other one, kind of like a butterfly. Now compare this with the Bohr orbits, right? In the Bohr case, we were just putting circles, but in the Schrödinger equation, like you can see, like the electron can do like much more complicated things than we imagine in the Bohr model. There's dz, also the radial part. So radial part, there is a little bit more to type, right? It's like some function, some Laguerre L, blah, blah. You don't have to be worried about this. What you want is to see how this function looks like. So this is the 1s, and you can see I, for example, multiply this with r square. If I didn't have that, I would have like something non-zero at the origin, but because of this r square, right, the volume of the space is shrinking as you go to r is equal to 0, then the probability to be there is 0 because the volume itself is 0. So I can put this r squared. This is 1s. I can look at R20R. You can see now, like Bohr model, or like these like semi-classical quantization we had, I have 1, 2 nodes, maybe 1 node here, the other one at infinity. This is like 2p, 3s, and 3p, 3d. You can actually put all of them together and compare which one falls faster, right? For example, this is 1s. This is the closest electron. It's closest to the nucleus. 2s is a little bit further away, but you can see there is like a peak close to, right? 3s is even further away. 4s is even more. Or you can compare 2s with 2p. You can see they are more or less the same, but 2p seems to be a little closer. 2p is a little smaller than 2s. You can do the same thing with, for example, I don't know. 3d is even smaller. 3d is closer than 3p, and 3p is closer than 3s. I think I have f here to f, the same thing. And for f orbitals, I have to go to 4. You can see 4 orbital is quite inside the nucleus. Even though I'm like in a bigger quantum number, the peak distribution seems to be very close. And then d, and then p, and then s. I mean, you can not only plot like pretty pictures like this, you can also integrate these things, multiply them, you can do whatever you want. And as far as I know, it's free. I think if you are an ODTÜ student, you can install it and use it, which I recommend strongly. Any questions? Then maybe we can give like a 5-minute break and continue.